Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So, on the 2nd of this month, when those Artemis II engines ignited, if you think about it, the astronauts strapped inside were protected by aerospace tech that, on a fundamental level, hasn't really evolved all that much since the Apollo missions.
No, it really hasn't. It's surprisingly old school.
Right. Because when you look at the schematics for shielding critical avionics from just the sheer hostility of deep space, the solution has almost always been brute force. You use thick plates of aluminum or layers of polyethylene.
Maybe water jackets, things like that.
Exactly. We're taking these incredible 21st century sub-nanometer computing architectures and, burying them behind 20th century dead weight. And if you know anything about orbital mechanics, dead weight is the ultimate enemy.
Well, absolutely. Every single ounce of mass we push past Earth's gravity well costs, thousands of dollars.
We're paying this massive payload penalty just to build dumb walls. But so what happens when that wall is completely reimagined? What if you could achieve the exact same protection, the same attenuation of all that cosmic hostility with a material that is thinner than a single strand of human hair?
Which sounds like science fiction, right? But the mass penalty isn't just an economic issue anymore. It is the absolute physical bottleneck for human expansion into the solar system right now.
Because rockets can only carry so much.
Exactly. The Walkett equation is just completely unforgiving. If half of your available payload is dedicated to structural shielding just to, prevent your onboard computers from getting fried by cosmic radiation, well, you've severely restricted the scientific instruments you can carry.
You're leaving behind life support redundancy.
You're leaving behind actual human crew members. The traditional paradigm relies on macroscopic, really dense materials to block these high-energy threats. But when you hit the absolute limit of how much mass you can launch, you just can't build thicker walls.
You literally can't.
Yeah. Right. You are forced to look the other way. You have to manipulate matter at the molecular level to completely change how the material interacts with those threats in the first place.
And that brings us to this incredible breakthrough from the Korea Institute of Science and Technology, or KIST. They've developed this highly flexible, ultra-thin nanomaterial that handles two very different and visible threats simultaneously.
Electromagnetic interference and neutron radiation.
Right. And before we get into the actual physical chemistry of how they built this stuff, which is mind-blowing, by the way, we really need to establish why these two specific forces are so destructive to modern technology.
Yeah, that context is crucial.
So let's look at electromagnetic waves first, because, we aren't just talking about static electricity here.
Far from it. Deep space, and honestly even low Earth orbit, is just saturated with these highly energetic, constantly fluctuating electric and magnetic fields. And to really understand why that is lethal to a spacecraft, you have to look at how modern semiconductors are built. We are currently manufacturing silicon chips with transistor gates that are just a few nanometers wide.
Which is microscopic.
Right, and they operate on incredibly tiny voltage margins. So when an energetic electromagnetic wave sweeps through an unshielded avionics bay, it induces parasitic currents in those microscopic circuits.
It's essentially pushing electrons around.
Exactly. It forces electrons to move where they aren't supposed to.
So it's basically introducing noise into a system that requires, absolute silence to operate correctly.
That's a great way to put it.
If a stray voltage spike hits a memory register, it can literally flip a binary 0 to a 1. And you end up with what engineers call a single event upset.
Which can be terrifying in space.
Yeah. Best case scenario, it's a minor sensor glitch. Worst case, it's a catastrophic navigation failure right in the middle of a critical orbital insertion burn.
And that is just the electromagnetic side of the equation. That's just a wave of energy-flipping logic states. The other half of this dual-threat environment is neutron radiation.
Which behaves completely differently.
Completely. Neutrons actually possess mass, but, as the name implies, they carry a neutral electrical charge.
Meaning they don't care about electronics.
Right. They do not interact with the electromagnetic fields of the atoms they pass through. They completely ignore the electron cloud.
Which means they fly right through the typical conductive metals that we would normally use to block electromagnetic interference. Like a copper shield might stop a radio frequency wave dead in its tracks, But a neutron doesn't even notice the copper is there.
It passes straight through until it makes a direct physical collision with an atomic nucleus. So when a high-velocity neutron slams into the silicon lattice of a semiconductor, it is a kinetic event.
It's physical damage.
Yes. Physicists call this displacement damage. The neutron acts like a microscopic billiard ball, transferring its kinetic energy to a silicon atom and literally knocking it completely out of its precise crystalline structure.
It leaves behind a physical hole, basically.
Exactly, a vacancy in the lattice. It creates what's known as a Frankel defect.
Yeah. So, okay, an electromagnetic wave is an energy fluctuation that causes electrical chaos and logic errors, while a neutron is a mass-bearing projectile causing permanent physical structural degradation of the hardware itself.
And this duality is the core engineering nightmare.
Right, because to block the electrical chaos, you need highly conductive materials. But to block the physical wrecking ball of the neutron, you need something entirely different.
You need materials rich in low atomic number elements, like hydrogen-dense polymers or very specialized isotopes that can actually capture the particle.
So historically, if you want to stop both, you're stuck trying to bond these disparate materials together, which creates these rigid, bulky, incredibly heavy composite panels.
Which are prone to delamination under the extreme thermal cycling of space, by the way. And, going back to our first point, they consume an enormous amount of your mass budget.
Which brings us back to KIST. Because this forces the researchers there to just abandon the macroscopic approach altogether. If you can't stack distinct layers of heavy materials, you have to find a way to engineer a single material that possesses both conductivity for the EM waves and absorption capabilities for the neutrons.
And they found that synergy using two very specific nanoscale structures, carbon nanotubes, or CNTs, and boron nitride nanotubes, BNNTs.
Okay, so a nanotube, for those trying to picture this, is essentially a single atom-thick sheet of material that's been rolled into a seamless cylinder.
Right, and because they are governed by quantum mechanical properties rather than, classical bulk physics, their characteristics are vastly amplified.
So let's talk about the carbon ones first.
Carbon nanotubes are renowned for their electron mobility. The electrons can travel along the tube almost without scattering at all, making them incredibly conductive.
Which totally solves the electromagnetic problem. The CNTs basically form this highly conductive network, creating a nanoscale Faraday cage.
Exactly.
So when an EM wave hits this network, the energy is coupled into those conductive paths, it's absorbed, and then safely dissipated as just a negligible amount of heat, rather than passing through to the sensitive electronics behind it.
So the conductivity handles the wave. But to handle the neutron, we turn to the boron nitride nanotubes.
The BNNTs.
Right. Structurally, a BNNT looks very similar to a carbon nanotube. It's that same cylinder shape. But instead of carbon, the cylinder is composed of alternating boron and nitrogen atoms.
And the really critical component here is the boron, right? Specifically the isotope boron-10.
Yes. Boron-10 is special because it has an unusually high cross-section for thermal neutrons.
Okay, let's unpack cross-section for a second, because it's such a vital concept in nuclear physics. And it can be a little counterintuitive. It isn't a physical measurement of the atom size, right?
No, it's not physical size at all. It is a measurement of probability.
Like shooting a basketball.
Exactly. If you imagine shooting a basketball, the nucleus is the hoop. Most elements have incredibly tiny hoops. A neutron will just sail right past them without interacting.
But boron-10 has a massive hoop.
A massively disproportionate hoop, yeah. The probability of it actually capturing a passing neutron is thousands of times higher than most other elements.
And what happens when it captures it?
When that boron-10 nucleus captures the neutron, it undergoes a nuclear reaction. It absorbs the kinetic energy of the neutron and transmutates. It actually decays into a stable lithium ion and an alpha particle.
Wow, so the threat is completely neutralized at the subatomic level.
Exactly.
The theoretical physics of these two materials together is just beautiful. I mean, you have the CNTs for conductivity and the BNNTs for neutron capture.
Yeah.
But here is the major hurdle in materials science, right?
Yeah.
You cannot just dump carbon nanotubes and boron nitride nanotubes into a vat, stir them up, and expect them to work together.
No, absolutely not. At the nanoscale, these materials are incredibly cohesive. They desperately want to clump together.
They agglomerate.
Right. They agglomerate into these totally useless bundles because of van der Waals forces.
And overcoming that agglomeration is where the KISS team achieved something really remarkable. They didn't just mix the two materials together. They engineered a core shell structure at the individual nanoparticle level.
Yeah, this part is brilliant. Through highly controlled chemical processing, they managed to sheathe the boron nitride nanotubes within a layer of carbon nanotubes.
So it's essentially a microscopic coaxial cable.
That is the perfect mechanistic analogy. In a coaxial cable, you have an inner conductor surrounded by an outer shielding layer.
Like the TV cables we used to have.
Exactly. Here, the outer sheath is the highly conductive carbon nanotube network, and the inner core is the neutron-absorbing boron nitride.
So the carbon exterior immediately engages and attenuates the electromagnetic waves, while that boron core sits inside, protected, just waiting to capture any neutrons that happen to penetrate the outer lattice.
They integrated a dual-threat defense mechanism into a single, cohesive architectural unit. It's so elegant. But even with this coaxial nanoparticle, you are still dealing with a fine powder, basically. And you cannot coat an avionics bay or like a lunar habitat with powder.
No, you definitely can't. It has to be suspended in a matrix. And that matrix has to be able to survive the sheer mechanical violence of a rocket launch, plus the extreme temperature swings of orbit.
Right, the vibrations alone would shake a powder right off.
Exactly. So the matrix they chose is a polymer known as PDMS, polydimethyl siloxane.
Okay.
It is a silicon-based organic polymer that gets heavily utilized in advanced engineering because of its siloxane backbone. Basically, it's made of alternating silicon and oxygen atoms.
And what does that specific chemical structure do?
It gives PDMS an incredibly low glass transition temperature, which means it remains remarkably flexible and elastic even in cryogenic conditions, which leads to the really astonishing physical specifications of the final composite. Because the KISS team took their core shell nanotubes and embedded them into this PDMS matrix. And the resulting material is thinner than a human hair, yet it can stretch to more than twice its original length without tearing.
But more importantly, it stretches without breaking the conductive network of the nanotubes inside it.
Wait, how does it do that? Usually, if you stretch something conductive, it breaks the connection.
Right, that's the percolation threshold at work. In most conductive elastomers, if you stretch the material, the conductive particles get pulled apart, the resistance spikes, and your electromagnetic shielding just completely fails.
But the nanotubes are different.
They are, because nanotubes have extremely high aspect ratios, meaning they are very, very long compared to their width. So they can actually slide and telescope past one another within the polymer matrix as it stretches.
Oh, wow. So they maintain continuous electrical pathways even while the material is being pulled apart.
Exactly, which means the shielding remains totally viable even when subjected to severe mechanical deformation.
That is incredible. And we should really look closely at the performance metrics they achieved with this because the numbers are staggering. The material successfully blocks 99.999% of electromagnetic waves.
Yeah, in signal processing terms, that is an attenuation of roughly 50 decibels. For a material thinner than a hair, reducing the transmitted wave energy by a factor of 100,000 is practically total isolation.
It just completely eliminates the threat of induced currents in the underlying circuitry.
It does.
So the electromagnetic attenuation is virtually perfect. However, looking at the data on the neutron shielding, it shows a reduction of 72%.
Right.
And I want to focus on this for a second, because if I am an engineer and I'm designing a redundant life support system for a deep space habitat, a 72% reduction implies that over a quarter of the neutron radiation is still impacting my hardware.
That's true.
So in a highly radioactive environment, isn't allowing 28% of the threat through considered a pretty catastrophic vulnerability?
Well, you have to look at how it's being used. If you are evaluating a primary structural shield, like the outer hull of a nuclear reactor, then yes, 72% is completely insufficient.
Right.
But we have to look at the mass attenuation coefficient. Traditional high-density polyethylene shielding requires several centimeters of thickness and significant mass to achieve a similar reduction. KIST achieved 72% attenuation with a layer measured in micrometers.
So it weighs practically nothing.
Its mass is practically negligible.
Okay, so the context is really the application. You wouldn't use this as the primary outer bulkhead of the spacecraft.
Exactly. You use it as a conformal coating. Because it is so incredibly light and flexible, you can apply it directly to the semiconductor packaging itself, or you wrap it tightly around the internal wiring harnesses.
Ah, I see.
It serves as this highly efficient, localized defense layer that stacks with the broader structural shielding of the spacecraft. So it allows the engineers to drastically thin out those heavy outer bulkheads.
You are buying an immense amount of localized protection without paying the massive payload penalty.
Precisely.
And it does all of this while remaining thermally stable from, what, minus 196 degrees Celsius?
Yeah, the temperature of liquid nitrogen.
All the way up to 250 degrees Celsius.
Yeah.
So the chemistry of that PDMS polymer matrix is really doing a lot of heavy lifting to keep those nanotubes functional in those extremes.
It is. But chemistry alone doesn't solve the integration problem. You have to be able to manufacture this material into precise geometries that fit complex hardware.
Right, because wrapping a wire is one thing, but coding an intricate sensor array is another.
Exactly. And the transition from a bulk material to a targeted application relies entirely on the manufacturing methodology. The KIST researchers didn't just cast this material into flat sheets. They actually developed an ink formulation using the nanotube PDMS composite.
An ink?
Yes. And they deployed it using direct ink writing, or DIW.
Okay, so DIW is essentially a highly sophisticated form of 3D printing, right?
It is, but it relies on the precise rheology of the ink. The material has to be shear thinning.
Okay, shear thinning, like how ketchup is thick until you shake the bottle.
That is actually the perfect example. The fluid dynamics are fascinating. When the composite ink is at rest in the syringe, it is highly viscous. It acts almost like a solid.
But the moment mechanical pressure is applied to force it through the microscopic nozzle of the 3D printer,
the shear forces align the polymer chains and the nanotubes, dropping the viscosity dramatically. It flows smoothly right out of the nozzle.
But then the second it leaves the nozzle and the shear stress is removed, the viscosity instantly recovers.
Right. It locks its shape in three-dimensional space without slumping or spreading at all.
And this specific rheological behavior is what allowed the researchers to print the material into a highly specific architectural geometry, namely a honeycomb lattice.
Which is where things get really interesting, because they discovered that engineering the material into a hexagonal honeycomb structure yielded up to 15% better shielding performance against both EM waves and neutrons compared to a solid flat sheet of the exact same thickness.
That is wild. A structure that consists largely of empty space is actually superior at blocking radiation than a solid wall of dense material.
It's because the geometry is actively doing the work. It operates on the same physical principles as an anechoic chamber, the kind they use in acoustic or radio frequency testing.
Oh, like those rooms with the foam spikes all over the walls.
Exactly. An anechoic chamber is lined with geometric wedges. When a wave hits those wedges, instead of bouncing straight back or pushing straight through, it is forced into a series of multiple internal reflections. It bounces back and forth between the walls of the wedge.
So every single time the wave impacts the surface of the honeycomb cell in this material, a fraction of its energy is absorbed by the carbon nanotubes and dissipated as heat.
Right. By forcing the wave to navigate a three-dimensional maze, you artificially elongate its path length through the lossy material.
You literally drain its energy through geometric impedance.
And that geometric advantage applies to the neutron radiation as well. Fast neutrons entering the honeycomb structure are forced into scattering events. As they bounce off the walls of the hexagonal lattice, they lose kinetic energy through moderation.
They slow down?
They slow down. And as they enter the thermal energy regime, that's where the boron-10 cross-section is the most effective.
Because it drastically increases the probability of capture. The geometry serves as a mechanism to slow the threat down so the chemistry can actually neutralize it.
It is a brilliant synergy of material science and mechanical engineering.
It really is. And because it relies on direct ink writing, the shielding is entirely bespoke. I mean, an aerospace engineer doesn't have to design their avionics around flat panels of shielding anymore.
No, not at all. If they have a highly irregular optical sensor array, they can just 3D print a customized conformal honeycomb structure that perfectly encapsulates the device.
And they could even modify the density of the honeycomb cells based on the specific radiation vectors that device will encounter.
The optimization of mass and geometry is total. It's a complete game changer. But, the implications of this core shell nanotube architecture extend far beyond translunar injection trajectories and orbital habitats.
Oh, absolutely. Because the extreme environments we are trying to master are increasingly terrestrial.
Yeah. Dr. Jo Young-ho of KIST, who led the research team, explicitly outlined the terrestrial roadmap for this.
Right. He categorized this development as a fundamentally new concept in shielding technology. One that, sure, establishes critical domestic production infrastructure for the space age, but also immediately translates to the semiconductor, nuclear, and medical sectors right here on Earth.
The semiconductor manufacturing industry is perhaps the most immediate beneficiary of this. The fabrication plants that produce the 3-nanometer chips we rely on are incredibly noisy electromagnetic environments.
Right, because extreme ultraviolet lithography machines require immense amounts of power, and they generate massive electromagnetic fields.
And shielding the metrology equipment and the laser alignment sensors from this interference currently requires massive, rigid isolation chambers inside the clean rooms.
Which take up so much space.
Exactly. A flexible 3D printable shield allows for much tighter integration and significantly smaller clean room footprints.
And the economic implications there are just massive, especially considering the billions of dollars required to build a single modern fab.
It's a huge cost saver.
But, I look at the medical applications and I see a much more visceral human impact. Like an interventional radiology or fluoroscopy, medical professionals are working in close proximity to actively emitting X-ray and radiation sources for hours at a time.
Yeah, the current standard of care for occupational safety in those environments relies on lead aprons.
Right, the heavy vests.
Lead is highly effective at stopping ionizing radiation because of its immense density, but that density comes at a severe ergonomic cost. A standard lead apron can weigh upwards of 15 pounds. Wearing that constantly leads to chronic fatigue, severe musculoskeletal issues, and debilitating spinal strain for surgeons and technicians over the course of their careers.
It's a huge problem. But now, imagine taking the physical principles KIST utilized here. While medical equipment often deals with X-rays rather than neutron radiation, the concept of a flexible, ultra-thin polymer matrix embedded with high-Z nanoparticles could completely replace the bulk mass of lead.
It absolutely could. You could weave radiation protection into garments that weigh no more than a standard neoprene wetsuit.
They would stretch with the surgeon's movements while actively dissipating electromagnetic interference from the surrounding monitors and neutralizing the ionizing radiation.
It completely alters occupational health in high-risk medical fields.
It really does. And that same logic applies to the energy sector, right? Specifically, the deployment of small modular reactors, or SMRs.
Yes, the future of nuclear energy really relies on shrinking the footprint of the reactor. But the instrumentation and control systems, basically the digital brains monitoring the core, they still must be positioned very close to the high radiation zones.
Right now, those sensors are shielded by inches of lead and borated polyethylene. But if you can conformally coat the sensor packages in a millimeter-thick, 3D-printed BNNT honeycomb,
you drastically reduce the physical volume required for the sensor array. It simplifies the reactor design, it lowers material costs, and it actually increases the thermal efficiency of the entire module.
So we are really seeing a convergence here, whether it's an SMR in a remote grid, a lithography machine in a clean room, or a communication satellite in low Earth orbit. The density of our electronic infrastructure is just increasing exponentially.
It is. We're deploying highly sensitive sub-nanometer logic gates into environments that are completely saturated with intersecting electromagnetic waves and high-energy particles.
And the era of relying on bulk mass to protect those systems is over.
The physics simply do not scale anymore. KIST has demonstrated that the solution lies in atomic architecture. By leveraging the quantum conductivity of carbon nanotubes and the vast nuclear cross-section of boron-10, they created a single composite that handles both the energy wave and the mass-bearing particle.
They embedded that core shell nanoparticle into a highly flexible siloxane polymer, ensuring the conductive network remains completely intact even under severe mechanical stress and cryogenic temperatures.
And finally, they bypassed traditional manufacturing constraints by utilizing shear thinning fluid dynamics to 3D print the material into an anechoic honeycomb lattice,
utilizing empty space and geometry to artificially elongate the path of the radiation,
multiplying the material's attenuation capabilities without adding a single milligram of mass.
It's honestly a masterclass in interdisciplinary engineering. It proves that when we manipulate matter at the nanoscale, we can fundamentally rewrite the rules of how macroscopic objects interact with the universe.
It's going to change everything.
Which leaves this fascinating, almost philosophical implication regarding our future in these extreme environments. I mean, for the last 60 years, the primary limitation to deep space exploration has been the fragility of our machines, like how to keep the computers from degrading under the cosmic bombardment without weighing down the rocket.
Right, that's always been the bottleneck.
But as material science advances, producing these ultra-thin, stretchable armors that render our digital hardware virtually invincible, well, the technological bottlenecks will inevitably fall away. And when the machinery is no longer the weakest link, the true limiting factor for our expansion into the solar system will shift entirely. It won't be about how we shield the spacecraft anymore. It will be about how we manage the psychological fragility of the human beings isolated within it.